want to look at a very common, but it is a special circumstance, and I want to look at the motion of a charged particle in a uniform magnetic field. And remember, uniform means constant, so it's a constant magnetic field, and the magnetic force is, as usual, the force is the charge that's moving there. Its velocity crossed into the magnetic field. What we know now is this is a constant magnetic field. And so I'll just write that as B naught just to remind me that it's a constant. It's constant not only in magnitude, but also in direction. And just so that I can draw pictures, I'm going to assume we've got a plus cube moving in this magnetic field. And I'll draw it so that the magnetic field is coming out of the page at you on this diagram. So let's look at the positive charge first, and I'll be firing it upward. Magnetic field is coming out of the page, and one can use the right-hand rule, V cross B. So V cross B gives me, for a positive charge, gives me a force, a magnetic force that's in this direction. And so the force will tend to make this particle not move in the straight line, but to veer off of it, going in this clockwise fashion. On the other hand, if I have a negative charge, so now if the negative charge, I still have V going in the same direction, magnetic field coming out. So V cross B is still to the right, but because it's a negative, since this quantity Q is negative, that flips the direction to the opposite direction. And so now then the magnetic force is to the left, and instead of going straight, the magnetic force, or the particle, because of this magnetic force pulling it, will tend to veer it to the counterclockwise direction. Well, that shows one really pretty nice application of magnetic fields. It's very easy to use magnetic fields, uniform magnetic fields, to determine whether or not the charged particle that's moving in it is a positive charge or a negative charge. And it really just depends on whether it goes clockwise when I'm looking down into the magnetic field, or it goes counterclockwise. Counterclockwise for the negative charges, clockwise for the positive charges with the magnetic field coming out at us. Another peculiarity of uniform magnetic fields is can be found by looking at how much work is done by the uniform magnetic field. I'll look at just the positive charge case. Negative can be done easily the same way. Same orientation. B is coming out of the page at me, and V is in the plane of the paper, and moving in the upward direction. And again, just so I can draw the picture, I've got the positive charge. Notice here that V, the force, if V upward, the force again is to the right, and it goes in a clockwise fashion. We have got it drawn. And now then what I want to do is I want to calculate the work. I know that forces in general can do work if the particle is, if whatever it is moves. And remember, the usual case, you had a block and you pulled this force, and as a result it got displaced by a displacement vector d, pulled at a distance d. And the total work done by the force F on this mass m, whatever the mass of that block was, is the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between them. And that, of course, is just the dot product, or the scalar product, that the work is equal to force dotted into displacement. I like to write the displacement as the distance moved, delta r, that it was displaced, so you can think of r d vector as delta r vector. And that allows me to go to infinitesimals a little easier. If I do an infinitesimal displacement, then this is not full work, but it's just an infinitesimal amount of work. I have the force vector dotted into an infinitesimal displacement. And that's in fact what I pulled for this formula here. but it's really just the definition of work. Now I know the only force on this is the magnetic force, and I know the expression for the magnetic force is just Q V cross B. And I have to dot that into dr vector. Uh, and then what I'll do is I'll multiply by an infinitesimal amount of time and divide by the infinitesimal amount of time. And the reason for that is this is the distance moved and the time dt times dt is just dr vector. But dr vector dt is just the velocity vector. And as a result, what you see is that the magnetic force, well, the vector cross product we've seen produces a force that's perpendicular to the plane of both V and B. So it's perpendicular to V and perpendicular to B is the direction of the magnetic force. But if I dot product the velocity into something that's perpendicular to the velocity, then the dot product has to vanish. Things that are at right angles to each other, their dot product vanishes by virtue of this cosine of theta becomes cosine of 90. And so we just get that there's no infinitesimal amount of work. It's zero. And so the amount of work along any path in this that the charge takes is caused or produced by the magnetic force anyway. I can add up all the zeros I want, but it still turns into zero. So it's kind of a surprising result in that the magnetic force doesn't do any work on the particle. So it does no work so long as it's a uniform magnetic field. And that's what we've got here. So thus a static constant magnetic field cannot do any work on the charge. Now that has implications in other ways, and I can draw something from your first semester work, and namely the work-energy relation, or sometimes called the work-energy theorem. And that says that the change in kinetic energy of a particle is equal to the work that was done on it by the external forces. In this case, the external force is just the magnetic force, and we found that that was zero. So the change in kinetic energy of that charge Q, whatever velocity it was going at, has to be zero. But if the kinetic energy is constant, remember kinetic energy is 1/2 the speed squared, and what that then implies, mass is constant, it's equal to a constant, so the speed of the object, the magnitude of the velocity has to be constant. So again, kind of surprisingly, in some sense, in a uniform magnetic field, the magnetic field can only change the direction that the particle is going. It can deflect it one direction or the other, but it cannot change the speed of the particle. The particle, as it gets deflected up here, has the same speed everywhere on that at any time. Well, we'll use that result to get some really pretty amazing applications, but we will do that in the next segment.